All right. Excuse me. The initial side is where you start. The measurement, which we'll use the Greek letter theta, lowercase theta. Looks like this. And messed it up. Like this. This we'll call the terminal side. So if you are swinging this way to the left, then you have a positive angle. So positive is counterclockwise. Initial side. So if we start here and then we come down like this would be a negative angle, negative theta. So negative is clockwise. Oops. Dang it. Okay. Now the other idea. So picture these angles happening on the X and Y plane, right? Do you remember plotting points on X and Y, right?
Yes.
So these angles are spinning around that same location. Okay, so picture your X and Y graph. Okay. All right. I know I'm a little messy here, but so this location right here is the positive X and Y, right? So we call this corner the first quadrant. I'm sure you're familiar, but just in case you forgot, this is quadrant 1. And the X and Y are both positive. Okay, so I'm just gonna put plus plus. So if I were to plot this, the location 1, 2, you'd come out 1 and then up 2, right? You put a little point. Okay. Quadrant 2 is over here. We go counterclockwise. Over here, X is negative, so it's negative plus. Quadrant 3, they're both negative. Quadrant 4, Y is negative, X is positive, right? Do you remember?
Yes.
So when I have an angle going, we'd be starting here. This would be the 0 angle. 90 degrees would be obviously up here, right? So positive 90 would be going up this direction, stopping here. 180 would be going all the way to here, right? You'd be flipping from here to there. 360, obviously you'd go from here all the way back to where you started. Okay. If you go the other direction, starting here, going the other way, those are negative angles. And we'll go into that more in a little bit. Also note that 1 degree is equal to 60 minutes, which implies that 1/60 degrees is equal to 1 minute. One minute is equal to 60 seconds, which means, so just a double arrow, which means that 1/60 minutes is equal to 1 second. We're going to use this information for these particular problems. So I'm just giving you a bunch of information, which we'll start using in a little bit. So when they ask us to go from degrees, minutes, seconds, we'll need all this information. Here's some more formulas. This is the formula for arc length. For a circle of radius r.
Are you looking for the remote and the batteries?
I'm sorry.
Oh, I'm sorry. I was dumb. I was not on mute.
Oh, okay. No worries. No worries. For circle radius r and a central angle of theta radians, subtends an arc. Subtend just means like it's sweeping across an arc whose length is S equal to R theta. So visually, this weirdo paragraph. What I'm trying to say is this. So if I have some angle, I go this way. The distance I swept across is S. The way you find that distance is using this formula, R times theta, where theta must be in radians, not degrees, which I'll show you how to change it in a sec. I'm just giving you all the formulas and all the topics from 6.1. Then I'll start going into the details, okay? You know the formula? 1 revolution is equal to 2 pi radians. I'm sorry. Yes. 180 degrees is equal to pi radians. 1 degree is equal to pi over 180. So if you want to go from degrees to radians, so let's say I give you an angle, they change 45 degrees into radians, use this conversion factor. So here's a note, degrees to radians, use this. One rad is equal to, or 1 radian is equal to 180 degrees over pi. Use this one for radians 2 degrees. That looks weird. They're almost done with the notes here. Let's see. No, wait a sec, because I need to turn the page. Now, you guys good on this page?
Not yet.
Okay.
What does that say? 1 revolution equals what?
2 pi radians.
Okay.
Okay, so the first sheet, this is the homework. You should see. This is the first homework I want you to do. It's due on the 5th or 4th or 5th of September. First few questions are just definitions. Look at the notes or look at the book. Put in the definitions, right? Stuff you should know already, and if not, it's okay. Just read that section. The part I'm going to focus on is the complicated math problems down here. Number 10 is pretty easy, right? 120 degrees. So what I want you to do is have a unit circle. Let me see if I can, well, yeah, I'm not on my computer right now. Let me find one for you. This is the one I like. I like this one. Let's see if it lets me paste this guy. Here you go. So look at the angle. You guys see the picture? The circle?
Yes.
So 90 degrees. So starting at 0 means you're right here on this x-axis. Going to 90 is right here, right? Which forms a 90-degree angle. That's why it's called that. 120 would be here. So from this, let me get my pen out. From here to here, the angle in question is a measure of, it's supposed to be a theta, 120. That make sense? That's what this means here. From here to here. 120. So I would print that out because you're going to be using the circle all the time. And I'm not going to make you memorize it. You're allowed to use this as a separate page on your exams, okay? My professor forced me to memorize this and memorize all formulas, and it was not fun. It's very hard. So, knowing that, where is 120 degrees land on, right? So you look at the circle and you say, oh, okay, well, that's quadrant 2. Where's 335? Well, that's right under 360, so it has to be quadrant 4. So you just check the circle. That's all you got to do. Does that make sense on how to do 10?
Sir.
Yes.
All right. Number 11 says sketch in standard position. Let's see here. Oh, which one? I'm sorry. Let's see the question. So standard meaning positive angles. So where's 30? Well, if I'm doing it correctly, or I should say positive, it's going to be counterclockwise right here. This is negative, right? A negative angle. So it's not in standard position. This one's in standard, this one's not. That's all you need to know. Does that make sense?
Yes, sir.
Now, that being said, negative 90 means I'm going from 0 to down here, right? Because positive 90 is up there. So you need to understand, well, how do I do this, right? Start at 0. If it's 90, well, you would go 90 degrees this way, counterclockwise. If it's negative, you go the opposite direction. That's it. All right. Is that straightforward?
Yes.
You see how you would do negative 150, right? Any questions on part B?
No questions.
Let me know. Maybe we can, it's no big deal. This one's a little more interesting because it's bigger than 360, right?
Mm-hmm.
So let's do that one instead. Do I have my circle wrong still? Yeah, so here we go. The 360 means I start at 0 and I end up right where I started. So that's 360. So what was it again? I forgot already. 390.
Yes.
So 390 would be 30 degrees more. Do you agree? That it would land right here.
Yes.
So the angle now in standard position would be this angle. 30 degrees. So 390 is equivalent to 30 degrees. You can keep spinning around and around and end up landing on one of the original angles. Okay.
Could you just minus 360 from 390 and the difference you would just use for your angle?
Yeah, that is the best way to do it. So once you see that it's bigger than 360, just subtract 360 until it's below and you're done. Okay. So as soon as you see that, you should be thinking, oh, that's too big. Subtract 360. Get your answer. 30 degrees is right there. This is the opposite problem. This is way too negative. So keep adding 360 until it becomes positive, and then you stop. Is there any questions on A or B for number 13.
Mm-mm.
14 talks about coterminal angles. So if you saw the videos or read the book, which I'm assuming you haven't because we couldn't get that stupid thing to work, so no worries. Coterminal means you have two angles that are the same, end up at the same location. I think that's the easiest way to think about 120 is the same as 480, it's just 360 plus another chunk, same spot. Negative 240 lands in the same place. So any angle that lands on the same place are all considered to be coterminal to each other. Does the definition make sense?
Can you repeat that one more time?
Let's look at the last example. Right, the 390. 390 is coterminal to 30 degrees because it lands in the same place. That's all it means.
Okay,
That makes sense?
yes.
So these three angles, 120, negative 240, 480, all of these three land right here. So if you were to like work it out or kind of draw it out or whatever, you'll see that it's the same thing. These three are the same. But we don't say necessarily equal, we say that they are coterminal. They land in the same location. Any questions on 14? Like 15 is going to be actual workout kind of problem. Let me switch back to the real quick before we get to that other complicated question. First example. Let me show you how to convert to radians and degrees. So part A, we'll just do one, I guess. Convert this guy 45 degrees to radians. So what you do, remember I said use the conversion factor, take the 45 and multiply by pi over 180. This will cancel the degrees. Right, so just reduce it and it's no longer degrees because the degrees cancel. So 45 goes into both, so you end up with 1 pi over 4. But if you looked at the unit circle, you should know 45 degrees is pi over 4, but this is how you do the conversion. You multiply by this, and you get to something like that. Any questions on the fraction stuff here? That okay?
Nope.
Let me know. No big deal. Convert the angle in radians to degrees. So let's go the other direction. The pi over 2. So you take pi over 2 and you multiply by 180 degrees over pi. So you get pi times 180 over 2 pi. These cancel, leaving you with 90 degrees. So now I'm in degrees. So I went from radians to degrees. So I want to make sure we do it once just in case you don't remember or it's weird. All right. Now let's do something more complicated. We'll convert an angle that's in degrees, minutes, seconds to just plain old degrees and decimals. So we'll do this guy here. Well, you know what? I'm going to the next page. You guys cool on
Oh.
this page?
No, I still need the equation. Hold on. 30 seconds.
Yeah, no rush. It's all good.
Okay, I'm done.
Okay. All right. Convert an angle to decimal. Basically, I'm saying when you have this format, degrees, 36 degrees, 13 minutes, 56 seconds. If I want to change it to just a plain angle, we're going to need this stuff. 1 minute is equal to 1/60 degrees. 1 second is equal to 1/3600 degrees. So the way you do it is break this into addition. 36 degrees plus 13 minutes plus 56 seconds. So is equal to 36 degrees plus 13 times 1 minute plus 56 times 1 second. That makes sense, right? 13 minutes is 13 times a minute. 56 seconds is 56 times a second. It's not weird. Once it's in this form, though, you can use these formulas to change it in just degree format. Excuse me. I need to take my allergy medicine. So 1 minute would be 1 over 60 degrees plus 56 times 1 over 3600 degrees. That makes sense? We just substituted the formulas.
Yes.
All right. So now just change it to decimals and we're pretty much good. 13 divided by 60, what is that? I don't know. 56 divided by 3600. Now we're all in degrees pretty much. So this gets us to 36 degrees plus 0.21667, I guess, plus 0.015556 degrees. To add them up, that'll be 36 plus 0.23222. And that's it. It's round to 2 decimal places. I know it's a little weird, but you see what we're doing, right?
Yes.
Let me know if one of the steps doesn't make sense. All right. Jeez. So let's convert the other direction. Having something in degrees, can you change it to degrees, but with that minutes and seconds component? Okay. Convert the angle to degrees, minutes, seconds. So here's the angle, 53.694. So what you do is kind of break this piece off. So keep the degrees, because remember, when you get to this format, right? This is a whole number. There's no decimals. No decimals. So we're going to be working with the decimal piece only. Okay. But this is still in degrees. So what you need to convert is know that 1 degree is equal to 60 minutes. And 1 minute is 60 seconds. So right here, this becomes 0.694 times 1 degree, which is 53 degrees plus 694 times 60 minutes.
Can you move your journal up?
Oh, yeah, sorry. One moment. So multiply this together. 60 times this will give you it in minutes. So this will become 41.64 minutes. But I don't want to deal with that decimal, so you cut that decimal off. Because a fraction of a minute is a second, right? So this is the second piece. So right here, you'll do 53 degrees plus 41 minutes plus 0.64 minutes, which will be 53 degrees plus 41 minutes plus 0.64 times 1 minute, which is 60 seconds, right? Running out of space here.
Can you move your journal up? Again.
Yeah. Need to adjust my camera here. I forgot something. Yeah, I wrote the same thing again. There we go. So 0.64 times 60 seconds. That's gonna be 53 degrees plus 41 minutes plus 38.4 seconds. So at this point, just write it in that format. Finally. So you need these formulas to solve this. Is there any questions on number 4?
I did have a question. Why would we be getting rid of the 0.4 in the 38 seconds?
We just kind of cut it off because it's a fraction of a second, you know. You just round down, basically.
Okay, thank you.
Mhm. Yeah, because we're only taking into account minutes and seconds, so.
So could you break it down further if you wanted to go to like milliseconds?
You could, but this format is only used in minutes and seconds. I think
Okay.
it's like nautical type stuff.
Oh, okay. I was just wondering, just because I see that 0.4.
No, I hear you. You could. When I say you round up, use the basic rounding rules. And if I'm wrong, let me know. I'm pretty sure you just round normally, but I don't, I could be wrong. Let me check. Let me see if I can find that. It's a very good question. Okay, cool. Yeah, I think I'm pretty sure it's just the if it's higher than 0.5, round it up. If it doesn't take it, let me know. Let's talk about arc length. Example 5, find the length. I believe it's 5, right? Yeah. Find the length S and area A of a sector. So basically, they give you like some slice of circle. They're saying that theta is pi over 4. And radius is 2 feet. So to find this distance, S right here, we got to do R times theta. Just make sure that your theta is in radians. So we're not in degrees, right? So we're good. It'll be 2 feet times pi over 4. So that'll be pi over 2 feet, which is approximately 1.57 feet. Just use your calculator for pi over 2. Okay. If you use degrees, then you're going to have something that's not really correct. Because radians is an actual unit. Degrees is something that we use just because it's handy. Don't use it for actual calculations like this. 1/2 r squared times theta is the area of a sector. So the area in here, right? That's A. We're going over 6.1, or we're about to finish 6.1. Monica. So R is 2 feet, so plug it in. R squared times theta. That'll be pi over 4. So the area of the sector would be 1/2 times 2 feet squared times pi over 4. So that's 1/2 times 4 feet squared times pi over 4, which is pi, it just so happens is pi over 2 feet squared. This is squared feet though. This rarely ever happens that you get the same thing for area and the distance. It's not, it's whatever. Excuse me.
Excuse me, I have a question.
Uh-huh.
Is this gonna be uploaded? Like, can I watch it later?
Yeah, I will. I'll send it probably tomorrow.
Okay, thank you.
Alrighty. One last definition and one last example. Piece of notes and one example. We'll call it a night. Linear speed. All right, so suppose that an object moves on a circle. of radius r at a constant speed if s is the distance traveled in time t on this circle, then the line, or I should say the linear speed, not line, v of the object is v equal to s over time. So basically this is the speed of you going around the arc. Does that make sense? So if you're traveling in an arc like this along that s distance, that's linear speed. To find it, you find the arc length, divide by time. Angular speed. We're not going to do a whole lot of this, but you'll see it in physics, and we'll go into it a lot more so. But I will define it because it belongs in pre-calc, in trigonometry. The angular speed, omega, of an object is the angle theta swept out and divided by the elapsed time. So omega is equal to theta over time. Okay. Yeah, the best way to think of angular, I have to double check here, is rotational speed. So like if you have, I don't know, how fast you're spinning, like a tire is spinning. That's the best way to think about of angular speed, because you have the angle spinning around. Versus this is the speed along the arc, the edge of the circle, the edge of the tire. So speed at the edge of the tire versus the speed of the tire spinning. Anyway, let's do an example. Oh, wait a sec. Are you guys cool on this page?
Yes.
So last example. Can call it a night. Sleep good tonight. Doing math late at night makes me go to bed real quick. 6 1/4 inches. So a 6/4 inch, I should say, circular saw. Rotates at 4,300 RPMs. Part A. Find the angular speed. Basically how fast the blade is spinning in radians per minute. Right, theta over time. So omega, sec theta over time, that's the formula. So basically you have to figure out, okay, what the heck is theta? I know RPM means rotations per minute, so the bottom is no big deal. 1 minute, right? That part's easy, the time. Theta though, what is one rotation? One revolution? What is that equal to? Do you remember?
Is it 360?
Yeah, but we have to use radians, so it'd be 2
2
pi.
pi.
Exactly, it's 360, but technically use 2 pi. So there's 4,300 revolutions happening, 2 pi's, radians, right? Every minute. So I'm spinning around in a whole circle 4,300 times in 1 minute. That's what RPMs means, right? We break it down to the basics. I go around 4,300 times in 1 minute. Hence 4,300 times 2 pi. Right, this is the revolution. Does that make sense? Where this came from?
So the revolution is the theta.
Theta is this entire part, but the revolution is the 2 pi.
Okay, got it.
Yeah, and this is just part of it, right? This is how many of them, how many revolutions, well, how many, basically how big is the angle, right? We're spinning around that unit circle a lot of times in 1 minute. That's all this is saying, right? We're just spinning over and over again. So punch into your calculator, that should be about 27,017 0.70 rads per minute. Any questions on how we found angular speed? All right, part B, last part. Find the linear speed. All right, so linear speed is arc length over time, which is the same as saying r theta over time, right? That's how we define arc length anyway. What is r?
The radius?
Yeah, the radius. In this case, you can look at the blade size, right? Is this diameter? How are blades measured? Across or radius? When you go to a store, go to Home Depot, you buy one of these.
I'm pretty sure it's across.
Across.
Right, exactly. So we'd have to put 6.25 inches over 2 for the radius, correct? That makes sense? I'm not using the quarter just because this is complicated enough. I don't need more fractions. We cool with this part? Okay, assume yes. Theta, 4,300 times 2 pi, right? So we did that a second ago. Okay. I think they tell us in the question they want it in feet per minute. Forget, but I'm pretty sure that's right. This will be 1 minute over per minute, right? So multiply all this garbage out. You should get approximately 84,430.30 inches per minute. How do I change this to feet or feet per minute? Because we got inches, right? What do we do?
What's how many feet are in inches? 1 foot equals what?
12 inches equals 1 foot.
12, yeah.
So multiply by 12.
Yeah, pretty much. If I want to cancel inches, we multiply by the conversion factor. 1 foot over 12 inches would cancel the inches, getting me to feet. So all I got to do to get to feet is divide by 12. And we're good. You see what I mean? The 12 comes from here, from the conversion factor.
Yeah. But I have a question for the formula, the 6.25 inches over the 2, where does the 2 come from?
Because this is a diameter. The blade
Okay.
diameter. So I need to get the radius. So I use this.
Okay, I got it.
So at this point, you get 35.86 feet per minute. So we had to do extra work because they wanted it in feet per minute, not inches per minute. Which I guess is fine. Whatever. Any questions on A or B? No, is that? All right, well, this is like the last question in that homework. I'm gonna extend 6.2 till later. So this section is due on the 5th. Okay,
Got it.
all right. Well, we'll stop here, guys. If you have any questions, let me know. I'll stick around for a little bit. If not, we'll see you next time.
Okay, yeah.